Hi, everyone. Thanks so much for coming to this last late presentation of the day. Just so you know, Baseband is a lot more fun than beer. So I'm going to talk about how to hack Shannon Baseband from a phone. So I'm Natalie Silvanovich, and I'm a team lead on Project Zero at Google. And late last summer, we started talking about baseband. Of course, a lot of people on the team had heard of baseband exploits and baseband bugs, but we weren't quite sure what the impact was or how to find them. So we started talking about doing a baseband hackathon. What we wanted to do was emulate a real attacker and figure out if there was a group of people who had experience finding and exploiting vulnerabilities in other things. How long would it take us to ramp up and find something useful to do with baseband? And what would the impact of that actually be? So the target we selected was one of Google's own devices, the Pixel 7. And the Pixel 7 uses Shannon Samsung baseband. The specific chip is the G5300. And when we started thinking about baseband hacking, I think the first thing a lot of people think about is software-defined radio. And we did get access to one, in case of emergency, in case there was a bug, we really needed to reproduce. But we found that using one involved a lot of skills that we didn't really have. So we ended up not using a software-defined radio. The other limitation was there's a lot of bugs that require compromising a mobile network or setting up your own base station, and we didn't do that either. We looked from the perspective of what if we're one attacker either on the internet at large or within physical proximity of the device. How could we, like this guy in this really bad clip art, reach into the other person's device and get their data or their phone calls or whatever is possible? So this was really a team effort. As I mentioned, this was a team hackathon. It was about 5 full-time people. So this is everyone who worked on the research I'm about to present. This is everyone who got that little baby of our exploit walking. So to start off, what does a GSM network look like? This is kind of a simplified diagram, very simplified. Pretty much, you have at one end, your phone, which is the victim, and it will either be connected over a GSM cellular tower, or data can come to it over the internet through a VoLTE-call. And a lot of traditional baseband hacking looks at it from this perspective. It's someone who is in proximity to this device, usually with a software-defined radio, trying to find vulnerabilities in the protocols that can be processed. And one problem with this is that as the GSM has evolved, as there has been 3G and 4G and 5G, most features require authentication. So it was really just the 2G attack surface we had available to us to find vulnerabilities in if you're talking about a proximity attack. So we considered that, and we did find some bugs in this attack surface, but it didn't seem to be that large. Now, I considered removing this bullet point from my slide because when I wrote this, I did not think there were any good ASN1 vulnerabilities, and then Amak gave a talk on it, and then Hao, in his presentation this morning, mentioned another one that Sharab had found. So Ahmad explained to me that what has happened is that he found the very last vulnerability in AS1, and they're all gone, which is why we didn't find any. So what really happened here is we looked into this. We believe it is accessible without authentication, but we did not find any vulnerabilities in this area. And if we had found one, it probably would have required an SDR to reach anyhow. So another attack scenario, which is the one we're not doing, is that you could compromise a network. started to think about this attack scenario. What if the attacker, instead of being in proximity to the device, is just another person on the network? I mean, sure, you can't exercise as much functionality as you could if you were the mobile network, or even if you were someone in proximity, but there still is like something left. This made me think of research I'd done previously into WebRTC. And if you don't know, WebRTC is basically the open source software that runs almost all mobile video conferencing. It is in browsers, it's in mobile applications, and the fundamental way it works is you have two devices that can talk to each other through some protocol, and that can be an SMS, it can be WebSocket, something like that. And they trade information, and they use this to establish a peer-to-peer connection, and then that's how video conferencing works. And even there are a few big systems that don't use WebRTC, for example, FaceTime and WhatsApp, but they still use a WebRTC-like technology. Basically, all video conferencing has converged on this design. And of course, I discovered that VoLTE is also just like this. There's a few differences, but still fundamentally, you have devices communicating, and then you have peer-to-peer protocols. You know, when you have the video going from one device to another, or the audio going from one device to the other, you know, you don't have a server in there making sure every frame is okay. A lot of this is just being transmitted from one device to the other. And WebRTC, when I looked into it, had many, many bugs. And then in 2019, there was this WhatsApp vulnerability found in the wild. And I know I have put this slide in like every presentation I've given for like the past 4 years, but it's because it really, really changed how I thought about fully remote vulnerabilities. So the way this vulnerability worked was, once again, there was this type of video conferencing protocol, and the attackers made a few calls, and in this protocol, they found a bug that they exploited and managed to compromise WhatsApp. Then this inspired me, and in 2020, I exploited some WebRTC vulnerabilities on Android, and I was able to compromise a lot of mobile applications with 0 clicks. This definitely worked on Signal, it worked on Google Duo, it worked on a lot of different mobile applications. So if this is so common, why wouldn't it work on VoLTE? So we started looking at the P2P Attack Surface, and this really varies among devices. There's kind of, 4 main protocols involved in setting up a VoLTE call. There's SIP, Session Initiation Protocol, which is transmitted through a server and does the very first steps of setting up the connections. There is SDP, Session Description Protocol, which is a text protocol that, this is also used in WebRTC, and it includes stuff like the crypto protocols, like the keys that are used for the transmission, that sort of thing. And then once these are exchanged, you start sending RTP from one peer to the other, and then RTP is the wrapper for codecs like H.264. And for some devices, this will all be in user space. For example, some Samsung devices I looked at were like this. But for the Google Pixel, except for the codecs, SIP, SDP, and RTP are all part of the Shannon baseband. So this was a lot of attack surface to look at. So I started off by dumping the baseband from a crash dump. And I'm not going to go through this. Amat, who gave a talk at this conference about a baseband, he also gave another great talk a long time ago about how to get started with Shannon reverse engineering. So I'm not going to go over this again. If you want to figure out how to do this, just read this presentation. And then once I had this loaded into IDA, it wasn't too hard to locate the SIP and the SDP based on strings, because both of these are string protocols. RTP is more challenging, and honestly, I've still been looking at this. I haven't completed the analysis yet. Now, the one big problem was that execution flow was unclear. you look at the baseband and there is so much code, and it is very difficult to tell, often, of the 3 implementations of a thing, are any of them actually used? And after thinking about this a lot and looking at the stuff in IDA, I eventually just found a bug and made it crash. And this is not an ideal situation at all, but it was a way to figure out what code was actually being executed and figure out what was in the remote attack surface. Now, I definitely needed better debugging, and I'm going to say this was not a solved problem. I think that we probably still all need better debugging for baseband. But here's what was available. So the modem would do crash dumps whenever it crashed, and you can actually do a crash dump even if it doesn't crash using an interface. This is the code you type into your Pixel phone, and it will open up a screen that will allow you to do a crash dump and copy crash dumps and all that sort of thing. And then once you have your crash dump, it's a tar file. If you untar it, it is full of a lot of super cool stuff, including the actual crash dump, which is just all the memory of the modem starting at this address. So unfortunately, I never did get logging working on this. There are some nice tools, including leaked Samsung tools and a tool called SCAT available on GitHub that will let you do logging on a Samsung device, but these don't work on a Pixel. So it turned out, unfortunately, that the best logging we could get going was just calling strings on this crash dump, and a little bit of the log, including registers and that sort of thing, is still in there. Once we got code exec going, this really helped the process. There was a lot more inspectability on the modem once we got one bug to work. So, yeah, how do we know what bugs can be practically reached? So this is a different question, even though it's the same question, which is, one question is, you've got all this code, how do you know what's actually executed? But then there's the other question of, you have this GSM network that may or may not filter stuff. How do you know if the proof of concept for your bug is actually going to make it through the network? And this varies per network, but I'm going to go through a bit of how I think about this. So when you think about it, you have these 4 protocols that are going through a mobile network, and the mobile network both filters and processes it, but typically they do this for a reason. They don't do it for fun, and I would say, honestly, most of the carrier networks I looked at, they didn't do this for security. Most of this was for functional reasons. For example, for SIP, because there is an intermediary server, that server always has to parse the SIP, and then they'll re-encode it with some of the fields of the request. SDP can be passed through, but typically it will be parsed in SIP as well, so that the network can figure out the properties of the connection and might do different things. Some protocols are completely peer-to-peer, and it's unusual for the network to decode them except in special circumstances. In this case, this is RTP and H.264. But unfortunately, something you might notice is that there is no overlap between P2P and zero-click. We have the 2 protocols that are zero-click, SIP and SDP, and those have to be processed by the server. Then there is RDP and H.264, but those you have to pick up the call. So those are one-click attack surface. So barring bugs, the only zero-click surface is SIP and SDP. So that's what we focused on. And just to give an example of how filtering might work, and this isn't any specific carrier, this is just, how this type of software generally works. Here's a sample SDP string. This is the sort of thing that will be sent from one device to another. And this final line is called the M line, and this gives some properties of the connection. In this case, this will be the voice that's over VoLTE. And the intermediary server will parse it. And one thing it'll start by parsing is this audio. And in SDP, there's only two possibilities for VoLTE. This can be audio or video. So when it parses it, this will probably be an enum, and it'll like be 0 or something. And then the port is an integer, so it'll probably keep that as an integer. And then there's this protocol, and that's the protocol that this stuff is transmitted in. And depending on the server, there is actually a limited number of protocols. So some of them will make this an enum, but some of them will make this a string. So let's pretend on this server it'll be stored as a string. Then let's say you had a bug that was a basic buffer overflow of a string. If it's in this part of the parser, that is probably not going to make it through the server, because there's only two possibilities, so it's probably an enum. So that means it'll either be an error or it'll just put a 0 in there, and you're not going to get this back. Meanwhile, let's say you find a bug in this protocol string. That might be okay. That might make it to the other side. So the more of these types of servers you look at and work with, kind of the more of a sense you get of what's probably going to make it from one side to the other. But generally, the more possibilities a field has, the more likely it is to make it to the other side, and you can use it to exercise bugs. So, yeah, this varies across carriers. One thing I observed is the carrier of the callee, the carrier of the attacker, matters a lot more than the carrier of the receiver, though some receiving carriers do filter a bit. The other thing is all these protocols have reserved characters too, so that's something to be careful about. You can have a string that says AAA, but for example, if the string or the bug requires a space or the bug requires, /n, that's probably not going to work either. So another thing we did was we loaded the baseband into a QEMU emulator. About 2 years before we started this project, a few people on the team did a baseband training by Marius and Dominic, and they created this emulator that you can use to load baseband images. And Yvonne on our team modified this so that it would load this image. And this isn't a full emulator. It won't pretend to be the device and interact with a base station, but it will allow you to execute single functions. So this was another way that we could test things outside of the network. If we were wondering, is the network filtering or is this actually a crash, we could run it through and get the pure execution and see whether the bug really existed in the code. Yvonne also used this to do fuzzing on various features. So we did find quite a few fuzz bugs using this. So, code review. Once we had the baseband in IDA, I looked at the SDP and SIP parsers, and we also fuzzed them, and there were lots of bugs. I'm going to go through kind of 4 real quality bugs that we considered using in the exploit. So, the first one is in this accept types feature in SDP. And what's interesting about this is an array, right? It's formats that are available, but you can put more than one in. But unfortunately, in the modem code, this was an array of a fixed length of 12. So this was a pretty basic overflow. If you made this array really long, it would overflow this buffer. And this particular bug, it's an overflow of strings. So the object that's put into the array is, a string, so it has a length in it, it has a bit of other data in it, it has a pointer to data in it. But this was still a pretty good overflow. And this was fixed in March. And then there was this bug too, which is basically identical with a different identifier. So this is, the names of the different chat rooms in RCS. And this is also same overflow. Then there was this one. And this is a configuration parameter in SDP. And this is the same problem, but this one actually has a really nice feature, which is that ASCII to int is called on every one of these integers, and they're treated as bytes. So this is a good overflow because, the previous one, it was overflowed with strings. Meanwhile, this one, you can overflow it with absolutely any value. And then finally, there was this bug in SDP. And I have an asterisk next to it because the previous three, most carriers would allow. Sometimes you have to tweak it a little bit, but most carriers, you could get it from one device to the other from a remote phone and it would crash. But this one, most carriers didn't allow. But the way this one worked is that there's FMTP, which is the format protocol, and one of the parameters is an integer. And as part of the intermediary processing, it would assume this was an integer and copy it into a size 8 buffer. And then that's a very simple buffer overflow. Now, I'm also going to give an example of a representative SIP bug. Yvonne did a lot of fuzzing on SIP, and I found about 7 bugs. And these ones were less likely to go through carrier infrastructure. I would say most carriers did not allow them through. So this is the sort of bug that I think would require a compromised carrier or a compromised SIP server for an attacker to be able to use. But they're kind of interesting. Most of them were simple string overflows like this. This one in particular, this AAAA in the VIA got copied into a 32-bit buffer, once again with the assumption that it was an integer. And that's a buffer overflow. Yeah, by the way, this one was fixed in April, but all of these have been fixed by now. So how'd you actually test these? One thing that's nice about these things, sometimes being in user space and sometimes being in baseband, is it's really easy to find a device that does them in user space. And then I used Frida to hook the user space stuff. And then Frida allows you to change the parameters to a function with JavaScript. So it's pretty easy, especially since the Samsung Galaxy uses an open source library called resip for their SDP processing. And I looked at it before. So I hooked that and changed the SDP. And then I had a phone that would send different SDP across the network. And 3 of these SDP bugs worked fully remote almost everywhere. Even internationally, I was able to, call a phone from America to Europe, and that other phone's baseband would crash. So this actually worked pretty solidly. So now the question of exploitation. So I'm just going to recap what are the capabilities of these bugs. What could we actually do with them in terms of memory? And there was the chat room and the accept type ones. And these were a fixed size overflow, and the size was about 140, and they were both the same size. So they would both overflow this buffer of about 40 bytes with a string. And then there was the second one, which had a much smaller buffer, which was about 16 bytes. And this one would be overflowed with integers you could specify, like actual bytes. And for both of these, the overflow size was controllable. So you couldn't control the allocation size, but you can control how much of it you overflowed. So what security features did this G5300 Shannon baseband have? So no ASLR, which is unfortunately pretty typical of these modems. It did have stat cookies. It had limited heap corruption detection, which I think actually helped us, because it did have a stat cookie, but the stat, or a heap cookie, but the heap cookie was always AAAAA. But to make things better, if you got it wrong, it just returned and never touched that heap chunk again. So this, sometimes it was bad, but most of the time, it, gave us a chance to try again if our exploit didn't work. So, this was very helpful. And then I read through a few other presentations with baseband exploits in them, and the NX stack and heap seemed to be new. I couldn't find a baseband exploit that dealt with this before. But so since I'm not sure when these Shannon processors have the non-executable stack and heap. So then we started looking at the heap, and this is a sample of a heap chunk. And here's kind of the 2 interesting features. On the right is the very terrible heap cookie. I've already talked about it, but yeah, that's where it is. But the other interesting thing is this heap ID. And what this ended up being is that this is an inline indicator of what algorithm to use to free this chunk. Which was good, because what's the rest of this? Slabbiness. And it's a slab allocator, and this is actually a problem, because slab allocators don't have any inline metadata on the heap, which means you can't do a traditional heap exploit. Instead, what you have to do is try and get that allocated to a specific object that then you overflow and do your exploit. And I have spent like many weeks of my life trying to get this to work in a fully remote context. And I've generally come to the conclusion that trying to exploit a slab allocator in a fully remote context is hard. Because in terms of execution time, the space between the overflow and the overwrite or whatever you want to happen is often inconsistent and quite long. Because unlike doing an exploit, for example, in a browser, you have no feedback, so you kind of just have to hope the thing's allocated, and then hope it's overridden correctly, and then hope the right thing happens. And that usually doesn't work. So instead, we looked into this heap ID and discovered that, if you change it, it will just use a different algorithm to free this. And this algorithm can, in fact, be a traditional Linux-type dynamic allocator. So what I call heap 6, because that's the idea of this heap, is an alternate heap allocator that's linked. And it does not have safe unlinking, so it was pretty good for this exploit. And here is pseudocode for how it works. What's even nicer about it is it frees the pointer, and then it actually looks for the header at an offset, which is interesting because then you can actually put in the chunk, if you're making a fake chunk, where you want the rest of the chunk to be, which can solve a lot of difficult overlapping problems. And then after this, it's just a classic unlinking. So my first attempt was to use the configuration bug. That's the one that can overflow the small allocation with bytes. And this turned out to actually not work that well. The problem was, so it was 14 bytes, and the smallest size this allocator could allocate was 32 bytes, which meant there was tons and tons of contention. And because I was fully remote, it was hard to control what got allocated next to it. And when I started this, I thought, oh, this is going to be easy. No matter what is next to me, it's going to be a heap chunk, and I can overwrite it. But what turned out happening instead was it was actually pretty rare for it to be active. Usually it was next to an already freed chunk, and then that would never get freed again. When I tried this, it was actually even a minute or two just doing this over and over and over before I got the overwrite. And so that wasn't great. And then, when you're doing something like this, then you're relying on, oh, I overwrite an absolute value with an absolute pointer. And then you're back to well, where do I put my shellcode? So I'm going to say this only kind of sort of maybe worked. So Yvonne had the idea to work with the other bug. And this one, the buffer was 120 bytes, but because of the specific allocator, it would be rounded to 256. There actually weren't very many different allocation sizes. And this gave more control because it was a lot more rare that there would be an allocation like this. But also, with this bug, you could actually get 3 allocations done in a row. And that's because with this configuration types, it first allocates this array for the configuration types, then it allocates the string for each type. So if you put in a really long configuration, it will be the same length, and then the string will be allocated right after it. So, and what made this even nicer is because of the way that this heap worked. What you could do is you would have these 3 allocations in a row, then you do the overflow, then one gets freed, and because you can move that header, then you can put that inside the string, and then have the string contents be the thing that got overridden. And just to make this a little bit clearer, this is what a POC actually looks like. And So you can see there's the array up that's like of length 41. So that's the first thing that will get allocated. And then these two long strings that are both about 128 characters long, they'll get allocated adjacently. And then you can see, then the overflow will happen as the actual pointers and strings are written into that array. And then I think where these queues are is actually where the overwrite happens. So it's actually in line where the two pointers are. So then we have an arbitrary overwrite, though it has the problem that all unsafe unlinking arbitrary overwrites have, which is that you have to write both ways, right? You know, you're overwriting next with previous, and then you're overwriting previous with next. So you can't overwrite something with a value that's not writable, or you're going to get a crash. So what we ended up doing was, not only does the baseband support all these different ID'd heaps, it also supports a debug heap and a not debug heap. So that means that there's like a big master pointer to what heap algorithm you're using overall that then has more pointers to all these smaller algorithms. So we ended up overwriting that pointer, the main heap pointer, and we did it at an unaligned address. So then it was possible to make it so that the write works both ways because we were using the most significant bit of the pointer that was already there and then just overwriting it, and then the part that was not covering the pointer didn't matter. And then that we used to call this gadget. And this, I think, is really cool. You know, if you've fallen asleep, I would suggest you wake up and listen to this part because I think this is the most interesting part of the talk. At least I thought it was really cool. So Yvonne was going through the baseband binary for interesting gadgets, and he found this, which is actually part of the ARM OS. So I think like every ARM processor will have this on it, and this function is called scatterload. And if you look at what it does, is it takes a heap buffer in as a parameter, and then it goes through the heap buffer, and it calls the first thing with the next three things as a parameter, then it increments, and then it does that again and again and again and again. So this is like amazing for exploitation, because once you can call this with the one heap parameter, like, you know, you're good to go. You can call as many functions as you want. I would say the only downside to this is that it is in ARM, not Thumb. So when you call it, you have to be able to do a branch exchange, or it won't call correctly. But otherwise, this was like, I don't know, maybe the best gadget I've ever seen. That might be exaggerating, but very helpful. So the next problem is that, sure, calling functions is great, but eventually you want to execute code. And the heap was still non-executable. And in this ARM core, the non-executable memory is controlled by the domain access control register, the DACR. And luckily, the modem had this gadget. So we were able to call this with parameter FFFFFF, and that just turns off all the memory controls. So at this point, it's not non-executable. Also, you can now read and write memory at any point with no exceptions, because this is all off. And of course, this is a double-edged sword. Once the exploit gets to this point, it's very difficult to debug, because if you're writing to an invalid address, it just like doesn't do anything and moves on. But still, this is a necessary step. And now we are execoding code off the heap. So now for shellcode. Well, there were a few forbidden characters, mostly the SDP control characters. Though something I noticed is this is also carrier dependent. There are some carriers that ban even more characters from SDP. But I ended up just writing shellcode by hand, avoiding these characters. It wasn't that hard. If it's a really a problem, there is a Metasploit module that does this. But so I was able to just write shellcode, put it on the heap, and use that gadget to jump to it. I say no length limit. You know, your carrier is eventually going to explode if you make it like 10,000 bytes, but no practical limit. One problem with the Docker thing is that it only works in one thread, which is the thread that you did the exploit in. So if you want to execute code in another thread, what you have to do is overwrite the source code in an executable section, and then from the perspective of the other thread, that's still executable even though it's been overwritten. So then you can execute code in another thread that way. So now the next question is, now what? And this is going to be like the worst proof of concept you have ever seen. So you can see Yvonne is sending a text message, but it's a different text message that arrives because we've overridden that function. So now the for real question, like what do you actually do with this, which is not overriding a text message with hack? So there's kind of two possibilities here. Number one is that you can just keep it the way it is in the baseband modem. I've seen in other talks, you can put a proxy in that, proxies the network connection and see where network traffic is going. You could probably listen to phone calls. You could monitor text messages, that sort of thing. But the other thing I've been looking at a bit and haven't really succeeded at is what's the possibility of escalating privileges to the application processor. And basically, so the way the communication processor communicates with the application processor is through a lot of shared memory. And this is written via PCI, and then the application processor will wake up and process it. So I think there's probably the potential for a lot of vulnerabilities here, just because this is such a big memory space. There's MSI interrupts, and there's also GPIOs. So a lot of attack surface there. I mentioned when talking about crash dumps that there's lots of cool stuff in there. One of the really cool things you'll find in there is all these shared memory sections. When it crashes, it will dump them for you. So if you ever want to play with this, that's a nice feature you can use to kind of figure out what's going on. So that's it. What did we learn from this? One thing we learned is that modems can be compromised with enough effort. And the definition of enough here was 5 of us for 2 months. By the time we finished our hackathon, we had basically done what we'd set out to do. We found that modems to be quite a bug-rich environment. I would say, having looked at a lot of mobile devices, having looked at Android and iPhone, I'd say this was like a step down from most other source. These bugs were kind of easier and more obvious than the stuff I usually find. Lack of tooling was a major barrier. I would say this is almost like trying to find bugs on an iPhone where you need a jailbreak, and if you don't have a jailbreak, you can't really do anything. It was the same here, that before we had this first exploit that could run code, there was a lot of stuff that we didn't know that we could find out more about once we had code execution. So we learned that fully remote baseband attacks are a possibility. When I started this, I thought that it had to be local, that you had to have a certain proximity and mimic a base station, but that's not true. These bugs worked fully remotely from another phone, so no expensive equipment and no proximity requirement either. And finally, Shannon mitigations have improved, at least since the last exploits I was able to find, but they are definitely still lacking. ALSR would be a big improvement. You might notice this exploit really leaned on the fact that all the pointers were hard-coded, and I think that if we'd had to have a leak as well and then dynamically do this, this would have been a longer effort. It might have been 4 months. It might have been 6 months. I think that really would have increased the effort. And finally, I think heap hardening is an urgent thing that needs to be done on baseband modems. There are no heap protections, and then there are bad heap protections, and then there are ones that make exploitation easier. And, if you can do one, I'd say don't do the one that makes attacks easier. So that's it. Thanks a lot, and I think I've got a bunch of time left for questions.